Okay, so carrying on, just to recall that the turning moment of a thing going around in a circle is force times distance from pivot. Don't forget, from pivot. Now, let's look at some balancing. So let's say you had a plank and a pivot, much like a seesaw, and you want to balance the thing. Now we'll ignore the seesaw, so let's ignore the actual seesaw itself. Okay, we're just looking at the moments created by the people. So this person here on the left will create a force going downwards, and this person on the right would also create a force going downwards. Now you can see that the person on the left, let's call him lefty, and we've got righty. Lefty is going to try and rotate the beam in a anti-clockwise motion, and this guy is trying to rotate it in a clockwise motion. Now for us to be balanced, we can say this. So write this down. All anti-clockwise moments must equal all clockwise moments. Okay, so in other words, if we actually work out the moment on this side, knowing as weight, so weight lefty, weight righty, if we work out the force which is the weight of the left multiplied by the distance of the left guy from the pivot, which is dl, will be the same as the weight of righty multiplied by the distance he is from the pivot. Okay? So here's your example here with Garfield and, I can't remember the dog, Ollie? Is it Ollie? I think it's Ollie. So they are each going to create a rotating moment, clockwise, anti-clockwise. So anti-clockwise moment equals clockwise moment. So anti-clockwise, F1 times D1 is equal to F2 times D2. So here's an example. Let's put on here a couple of stars. So we'll put on a red star, put them there, and we'll put on a purple blue star, put it there. Put in some dimensions and weights. So let's say this one was 10 kg, this one was 20 kg, and put in some distances. So this guy is, oops, oh no, put that back, get rid of that, try again. So this guy here is, how far do you think? Let's say 1.5 meters from the pivot. This guy is 60 centimeters, so 0.6 meters. You notice that I'm always doing things in meters, okay, and that I'm always taking distances from the pivot. So now what is the anti-clockwise moment? So that's the guy who's going around this way. It's going to be equal to the moment that way. So anti-clockwise moment is equal to the clockwise moment. The force is provided by the weight, which is equal to mg. So 10 times 10 makes 100. This guy's weight will be 20 times 10, which equals 200 newtons. So, anti-clockwise moment, 100 is the force, multiplied by 1.5 meters. It's going to be equal to the other side, which I should really, have said I don't know that distance. Oh, silly man, silly man. Okay, we'll put that question mark there. The other side will be 200 multiplied by some unknown distance. Okay, so how do we work this out? Well, you work out all that side first, so do 100 times 1.5, and so you should be able to get that one, and then you're going to divide it by the other side there, because you want to divide each side by 200, so 200, cancel it on that side, and you divide it on this side. So 100 times 1.5 divided by 200 will give you the unknown value. Sorry about that with that mix-up. So what we're going to do in class, we're going to use a ruler, a pivot, and a 50-gram mass. Okay. Now, what we're going to try and find is the mass of a pen. So we're going to put a pen up here, try and balance it, making sure that the ruler is on the 50 centimeter mark, so we can ignore the mass of the ruler. And comparing the two weights, we should be able to find the mass of the pen. Why is things in equilibrium? Because anti-clockwise moments equals clockwise moments. Okay, there's an equal spread of force on each side. Okay, so we need two conditions for equilibrium. Okay, essentially we need to have one, that all forces are balanced. So remember, if we had a block, 50 newtons pushing on one side, 50 newtons on the other, that's an equilibrium. Second, all moments must be balanced, and that's what we've just talked about. What are some examples in real life? Okay, well, anything in real life essentially follows these rules. Okay, so someone, let's say, planking, you know, the good old planking from years ago, not done anymore. So this person is planking on top of a stool, or let's say just a block, okay, or a brick wall. Here we go, brick wall. Okay, there's my brick wall. So he's planking on top of this brick wall. Now, for this person to be in equilibrium, in other words stationary, the force of his weight is going to be opposed by the reaction force from the wall. So W equals R. So that's the forces are all balanced. The second one, his moments must be balanced. So this part of his body, the moment from that part will be equal to the moment from that part. So ACWM equals CWM. But there's a lot of examples in real life of this. Like another classic one would be some sort of mobile where you have different things hanging off and a different number of branches.